make it.
Oh.
And he will present us some of his experience in deploying differential privacy.
Okay. All right. Thanks for coming out here, and actually I'm going to thank the audience this time. Thanks all of you for participating in this workshop and making it a success. My name is Ashwin. My last name is Machanavajjhala. If you don't take my course, you don't need to know how to spell it. All right. I'm going to talk about some of my experiences in deploying differential privacy in sort of mostly in statistical agencies or in collaboration with statisticians and social scientists. And I have sort of two very ambitious goals for this talk, which I probably will fall short of. And the two goals really are, for practitioners in the audience, sort of highlight what are the important steps in deployment of differential privacy in statistical agencies and in other agencies as well. And maybe sort of mention some of the tools that they can use. Maybe we've heard a lot about the tools that people can use that have arisen both from the statistics community and the CS community in the last few days, and we'll hear more today and tomorrow as well. But I just wanted to sort of, that's one goal, and the other goal is basically for the privacy researchers in the audience. What are some sort of open questions in CS and stats which sort of arise when you actually start deploying differential privacy, and maybe I feel like some of these problems we've not really thought too much about, or we've thought about them, but they still are sort of open problems. Okay, and the goal of this talk is to be interactive. So if you want me to, please stop me with questions. I don't need to sort of finish everything that I have. Okay, all right. I'm going to start with this. This is what I call is a checklist for deployment, which sort of typically is what you need to do when you're going around and trying to deploy differential privacy, which is basically, to start off, like before you even think about privacy or anything, you need to really know what your data is. Right? Know what your data is. Don't try to force fit it into a single table, but basically understand what are the entities in your data, what are the relationships, and also more importantly, sort of formulate its uses. Where are the data being used for? Right? What are its uses? What do people care about? And I think it's a very, very important task before you even go into the process of deploying differential privacy. Right? And then once you know what your data is, I'm going to talk a little bit about what I mean by designing your privacy model. Right? Differential privacy, the original definition at least sort of thinks in terms of a single table. When your data is a little more complex, you may need to think a little bit about how you sort of set up your differential privacy for the problem. I'm going to talk a little bit about that. And then once you set up your privacy model, then you can sort of start thinking about designing algorithms. And we've heard a lot of talks about how you design algorithms for differential privacy. And finally, and this came up, I'm very happy it came up a lot today in today's talk, is really understand how do you develop methods to sort of estimate error in the release data, communicate the error in the release data, and take that into account in your downstream analyses. Right? And so today's talk, I'm just going to talk a little bit about these three aspects, so designing your privacy model, and I'll sort of mention some work I've did with the US Census Bureau. Some of you may have heard about it already. Then I'll talk a little bit about designing a differential right algorithm, and I talk about some of the questions that are sort of still open, technical questions that are open in the space, and finally I'll talk a little bit about developing methods to sort of estimate error, and in particular about sort of privately verifying error in mechanisms. Okay, all right. So for the first part, the sort of the running example I want to use is this product that the US Census Bureau releases called On the Map. Several of you might have heard about it. But basically, it's a product where data is collected from censuses, surveys, and also administrative data, and they are linked. And these data are then published on this sort of on this interactive website, which allows you to learn where people work, where people live, what their jobs are, what their salaries are, what their starting and ending dates of their jobs are, and so on. Okay, so here is an example visualizations from this product, and there's several interesting uses for this data set. One kind of use case is basically for resource allocations in certain kinds of situations. So one use case on the map has been for emergency management. So when you have like a hurricane or a snowstorm, right? So several individuals are no longer able to either go to their jobs or are affected. And so there is a process where you have to sort of determine whether a certain region in the US, either a county or a civil division, has to qualifies for support from the government, right? And so therefore you need to sort of tabulate how many people and of what categories are affected by that emergency. Right? And this is one of the use cases where these data are used, because it sort of tabulates up how many jobs were affected by a certain thing, like in this case a snowstorm, I think. Okay? All right. So that's the use. So what does the data look like for this one? The data looks like this. So basically it's a for those of you who don't know what this is like an entity relationship diagram, which is typical when you store data in relational databases. You have three kinds of entities here. You have employees, which are people. You have employers, which are businesses, and you have jobs. And so according to this, each employee has a job, and each employer, in particular, you're looking at the primary job, and each employer can have multiple jobs. Each employer can employ many employees. Right? And there are attributes associated with each of these kinds of entities. Okay? And the goal here is to sort of release these tabular summaries. So you want to release sort of things like counting queries. So how do you count counts of jobs held by workers of age 30 who work in the city of Boston? Marginal queries of the form counts of jobs held by workers of age 30 across different work locations, and so on. Right? So the goal is this. And the goal here was to release statistics that can allow you to tabulate answer these kinds of counting queries and tabulate these kinds of marginals in such a way that it sort of preserves privacy, right? So in this piece of work, rather than sort of directly saying, okay, we're going to use something like differential privacy, we said, okay, let's look at what the privacy requirements are. Okay, so what are the privacy requirements here? The privacy requirements for the US Census Bureau stems from Title 13, Section 9, and here it basically says essentially that whatever data is being published by the US Census Bureau should be in such a way that it doesn't identify particular establishments and particular individuals. So not only should we think about the privacy of individuals, you have to think about the privacy of establishments as well. So here's an example where you have to think about privacy of multiple entities that are there in your database, right? And of course, it comes with like heavy fines here for every violation. So remember, like, for every record that you sort of harm, this is the kinds of fines that are applied here. Okay. So of course, this is very succinct. There's nothing really it's very hard to glean something completely out of this, right? And so what we did in this scenario was we actually looked at what the current interpretation of the law was. And this law has been interpreted by the US Census Bureau, in particular by disclosure review boards, for several decades. And so based on that interpretation, we were able to sort of glean sort of privacy requirements. So in particular, we were able to glean three sort of privacy requirements. One is basically that the existence of a job held by a particular individual must not be disclosed, right? And sort of in words that sort of make more sense to us, it was sort of like you don't want any exact re-identification of employee records by some sort of an informed attacker. Yes?
Does that mean you don't want to know that there's a janitor, or you don't want to know that there's a janitor whose name is Aloni?
By a particular individual.
On this start date and end date.
Existence of a job held by a particular individual. By a particular individual. So you should not know that this individual held the job of a janitor in this company, right? So that's the. And it doesn't say anything about time. So particularly, it could have held it at any point of time, but you should not be able to tell that Aloni was a graduate student at MIT. Or at least that's the interpretation. And the other interpretation basically was that the existence of an employer business in almost most cases, as well as its type or sector, and location is not confidential. These are physical businesses that actually physically exist in some physical location, because if you look at the schema before, there was an address or a geography associated with that thing. And since these are businesses with physical locations, presumably you can go and check that it exists. So the existence of this is not confidential. You don't need to hide the presence or absence of an employer. But the data on the operations of this particular business must be protected. And this is where basically the kind of interpretation that they had was sort of different from what we usually think of what the interpretation could have been. But essentially the interpretation was that there is some sort of aggregate properties of this business, like for example, the number of employers, the number of employees of a certain type, and so on. And so you don't need like perfect secrecy of that. You don't need to perfectly hide how many employees are there in that employer, because again, if you know what the business is, then you probably know roughly it's a big business or a small business. But rather what you want to do is you want to basically have sufficient uncertainty about the size of that business. So in particular, the uncertainty of up to some sort of multiplicative factor of this on the workplace of an employer. Okay. And so what I want to sort of talk about here is really, what I want to stress on here is that it's good to know what is the basis for privacy in an application, because that sort of gives you some sort of starting point to think about what is the appropriate privacy for an application. Okay. So in this case, we got this, and then we said, okay, let's take these and run with these, and that's what we are trying to sort of protect. Okay. So this is differential privacy. There is a definition of differential privacy. I'm just going to define it just because it's a differential privacy talk. That essentially what differential privacy, the original definition says, is that for every pair of neighboring tables that an algorithm operates on that differ in one row, in the presence or absence of one row, and in this case this red row is missing, and for every possible output this mechanism can generate, in this case, your attacker should not be able to distinguish based on this, whether it came from D1 or D2, and mathematically it's formulated as the log of this sort of odds ratio is bounded by epsilon, right? Now in our setting, what do these neighboring tables, what should neighboring tables look like, right? Because we have multiple things that you don't have a single table anymore, you have multiple tables. Any database is 3 linked tables now, right? And in which ways should these one set of 3 linked tables be neighboring to another set of 3 linked tables, right? Based on the constraints here, we could naturally come up with something, right? So in this case, maybe the neighboring databases could be of the form that in one case, one employee works at Uber, another employee works for Microsoft, or in another kind of neighboring databases, like one employee works at Microsoft, another employee, in the other case, the employee is just unemployed. Or another way is like in one case, an employer, say Uber has 1,000 employees, in another case it has 1,050 employees, where alpha is 5%, and so on, right? So you can set up your privacy like that, and then you can check differential privacy. But now the question is, why does this law match this kind of a definition, right? So when your definition is sort of nice, it has very nice semantic interpretations in terms of the fact that anything an adversary can, any informed adversary with some sort of prior over databases, right? Whatever they learn here, they can learn in the case where one of the records in the database has been removed, or one of the records in the database has been added, right? You can get nice semantic interpretations when you have sort of this kind of neighboring databases or another variant of differential privacy. What do the semantics look like? And so we need some sort of understanding of that. So one way to sort of get that kind of understanding is using the what you call the Pufferfish Framework. And it sort of thinks about privacy slightly differently, but it allows you to be a little more flexible, right? And then the Pufferfish Framework, basically what we can say is, rather than talking about neighboring tables, we can talk about what is being kept secret. So this is determined as a set of pairs of statements over a database or a domain. And these are sort of mutually exclusive pairs of secrets of the form like, in one case, Bob works for Uber, in another case, Bob is unemployed, or in one case, Uber has 1,000 employees, and in another case, Uber has 1,050 employees, and so on. And And basically the goal is to sort of make sure that a certain set of chosen adversaries can't distinguish between them. So these are sort of sets of what we think of as data evaluation scenarios, so the way data was generated. You can also think of them as adversarial priors. And the goal is to make sure that for every adversary and for every pair of the discriminative secrets, the posterior odds of one secret versus another secret, after you see the output of your algorithm, should be close to the prior odds of the ratio of these secrets. Okay? I'm not going to go into detail about like the theory behind it, but basically the advantages of this is essentially the privacy is defined more generally in terms of customizable secrets rather than records. And now your privacy definition can take into account things that you're releasing, like for example in a relational database you have constraints between tables. So you know, a foreign key, which means that if you remove if employer record is removed, then all of the employees in that should be removed from the jobs table. So you can have those kinds of constraints, and we can sort of tailor the set of discriminative secret pairs to things that we really sort of care about, right? And so in this work, basically what we did was basically we were able to take these laws and mathematically write out these privacy requirements in terms of sets of adversaries and pairs of secrets, and then show that the neighboring definitions that we came up with actually imply those, and then design algorithms to satisfy those. Okay. Yeah. Question?
Just one.
Yeah.
So what you just said was you took the law, you expressed it in terms of pufferfish, you show that DP implies the pufferfish.
Yes, it implies.
DP is sufficient for the law, right?
It's sufficient, yeah.
Presumably what you would want to do is, if you really think that the pufferfish is equivalent to the law, and since pufferfish is probably easier than DP, you want to have algorithms that only give you pufferfish.
Yeah, I'll come back to that. Yeah. That's a hard problem.
I see.
Yeah.
So then,
Yes.
all right.
I'm sorry?
No, nothing. Oh, wait.
I'm sorry?
I will wait. I'm sorry.
Your question was what was gained? No, what do you mean what was gained?
No.
No, so what okay, let me say one thing. Let me say one thing. So the gain that you get here basically is like it's not directly differential privacy, right? The definition here we have is like some weird combinations of neighboring databases. Like you can come up with whatever combination of neighboring databases you want, right? Like for example, if I have a location stream or sensor data, right? I could say I'm going to protect privacy where neighboring databases are your location at some second or at some nanosecond. Is that a good notion of privacy? Probably not, right? And the reason that probably not is basically where these semantics will tell you that if you do it that way, then essentially the only kinds of secrets you can't distinguish is your location at a nanosecond. But if you're even interested in your location over this period of time, you will not get any kind of guarantees, right? And that's the reason why, that's what this gives us. That's the gain you get. Make sense? Yes.
Can you say in words about how you think about matching the adversary, the data evolution scenarios with the law, or?
All right, I was hoping not to get into it, but since you raised it, I guess I have to. All right. Okay, so this is the subtleness about defining privacy, right? And there are two ways in which you can define the semantics of privacy definitions, right? So one way is to think about in terms of you have adversaries who have some priors, and you're looking at what is the likelihood of what is the likelihood of the posterior likelihood of some property given the output, right? Versus what is the likelihood of some other property given the output, right? And if you want this kind of a privacy guarantee, there are always sort of arbitrarily bad priors under which you can get no kinds of bounds, right? The other way of doing it, so therefore you have to necessarily make some kinds of assumptions on these priors. In this particular scenario, the kinds of assumptions we made were basically that in this case, what kind of assumptions we made were basically like the attacker doesn't know correlations between different employers and their workforces, and then conditioned on where an employee is working, then there are no correlations between employees. you sort of have to necessarily make those kinds of assumptions. The other kind of semantics that you can think of are the simulation semantics. And so for the simulation semantics, the way it works is basically you have an attacker who has some knowledge of the data generating distribution of the data set. You draw a data set from that, right? And you look at the posterior likelihood of some property. And you compare it to another scenario where you draw the data set, but then you take this actual sample of the data set that you've gotten and you act on it and remove a record. Okay? This is different from drawing the probability of drawing a database where that record doesn't exist. Right? In fact, the database where you acted upon it and removed that record may not even be possible from the distribution that you've drawn the data set from. Right? But under that kind of a simulation semantics, you can show it doesn't matter, no matter what the prior is, this sort of ratio can be bounded. Right? So these are two different ways of sort of thinking about privacy. And it'll be nice to have a way to marry them, because in this semantics, we can think more generally about sets of sort of discriminative pairs and so on. In the simulation semantics, unfortunately, or at least for me, how you model these sort of secrets very heavily depends on these modification strategies. Like what kind of actions can you do on the database, right? And I think some work needs to be done on understanding what is the right set of modification strategies that can match with the notion of keeping something secret. That is one. The second complication comes in when your data evolution scenarios may need to incorporate exact constraints in the data. So if you go back to Monday's talk about how the census has to release data and in addition release exact invariants, right? So again, you can do two kinds of analyses here in the simulation space, right? In the simulation, one kind of argument you can basically make is essentially that I am acting on the database without looking at the invariants at all, right? Not only can the database not be possible to be generated from the distribution, it may not even be matching the invariants, right? Then the kind of guarantee you will get is like, yes, I can bound my sort of disclosure, but essentially you're saying it's not the fault of the differential privacy algorithm, but you could get sort of disclosure through the invariants, right? But if I am sort of Census Bureau and I'm releasing both of these, I want to really know what is my overall privacy loss. And then like you have to really be careful about thinking about under which modification strategies can it make any bounds. And this is a very, very tricky problem, and this is something that we are sort of thinking about, and I think there needs to be more work here. And yes, so we can discuss this offline.
So since a little push this button.
Now I can get to the next slide, but if we don't get off the button.
Still.
Two comments or questions. One is the existence of the invariant seems to already destroy the assumption of independence, because
no, but you can if you have invariants, then you will basically condition, like if you use the pufferfish semantics, you would be something like independent conditioned on the invariants or something like that, right? So you will say that you have an invariant, you basically, that is true, and then every database that you generate will have that invariant in it.
I don't see how to do that without creating dependencies.
Yes.
And the other one is that for the same reason, this is probably not going to compose well, this definition.
Not every definition under pufferfish will not every definition under pufferfish does not compose. There exist large subclasses of it which compose. But again, as I said, every sort of pufferfish definition does not mean it's a good definition. But that just follows from the fact that I could construct a bad set of neighboring data set and give an explanation for it. So this is a good way to think about explaining what your privacy notion is, and then you can decide, is it a good explanation, is it a good definition or not, right? If the set of adversaries you can protect against is really small, then it's probably a bad definition, right? If the kinds of, for the secrets you care about, if the bounds you get are very bad, then again it's a bad definition. Pufferfish does not tell you that every definition you generate from here is good. It just gives you an explanation for the definition. I'm going to move on at this point, and I'll take more questions in the break. Okay? Marco, how much time do I have?
let's say a little more than 10 minutes plus question.
Nice. All right. So the other important point I want to raise here was we did something that a lot of people do not do, which is think about utility cost. And I think we need more papers that think about what this kind of a utility cost. So what do I mean by utility cost here? So in this case, there already existed a mechanism for releasing the data, right, based on existing SDL technology. And now we are proposing a new algorithm that has some sort of formal privacy guarantees. And so now you want to ask not only whether the mechanism that you generate has good accuracy properties, but also in comparison to the previous SDL techniques, which obviously also has some error guarantees, like how does it compare? Right? And in some sense, you are getting more now because your privacy guarantee gives you transparency, it gives you provable guarantees, and so on. So you want to sort of see what are you losing in terms of accuracy or utility for the gain in terms of the privacy properties. And since I have not too much time, I'm just going to say that in a lot of settings the settings of epsilon, and since you have two entities, you have two different privacy loss parameters, one for employees and employers. For various different settings and across different algorithms, we could actually find lots of cases where we had lesser error than the existing SDL technique for the tasks of releasing sort of reasonable dimension marginals, but then, and in some cases, we were only up to 3 times worse. So I think this was this is an interesting result. It basically says that there are cases where you can actually do as well as SDL techniques. It's not like differential privacy or formal privacy technology will lead to a loss in accuracy compared to SDL. And this is something that has to sort of sink in. We should do more of these experiments. We should show more of these comparisons. Because I think for a large number of tasks, our differential privacy techniques do very well. Okay?
What are the different lines on that?
Yeah, so different lines are basically, there are 2 kinds of parameters here. One parameter corresponding to the person, another parameter corresponding to the employer. So essentially, different lines correspond to the x-axis corresponds to the privacy of the individual, and the line here, these points correspond to the privacy of the employer. And so when you have, as this alpha increases, you get more privacy for the employer at the same cost, same level of privacy for the individual. Okay. All right. So the takeaways here are basically, there are a large class of tasks for which you can that can be accurately performed using differential privacy or variants of differential privacy, and in some cases more accurately than SDL techniques. And we definitely need more such empirical comparisons in such evidence in the literature so that we can show that this is doable. The other thing is basically, I think, and this may be a little controversial, but basically a careful analysis of privacy requirements can help design mechanisms with better privacy utility trade-offs, right? And I want to point out that real data is rarely flat, right? Real data is very relational, right? Here is somebody mentioned Mimic yesterday, which is like an EHR data set, right? It has 43 tables and 63 relationships between these tables. It's super complex, right? And you have entities of all kinds of types. You have people entities, there are patients, you have admissions of patients, you have lab entities or caregivers, you have all kinds of sort of entities. And now thinking about whose privacy do you want to guarantee is an interesting question. Do you want to guarantee privacy of the patient or the entire patient's record? Do you want to guarantee privacy at the level of an admissions of a patient? Do you want to guarantee privacy of caregivers? And it may be very important that a caregiver should not be leaked out that a caregiver is, for example, giving care for Tom Cruise because they may be hounded by the paparazzi, right? And so it's important to sort of think about at what level you want to guarantee privacy. And based on the application, your privacy what you choose to associate privacy with is going to be different. And now neighboring databases are going to be more than just sort of adding or removing a row from, say, one of these tables. Okay. There are open questions here. I'm going to sort of basically say that this discussion, we had a long discussion about invariants and semantics, and that's very hard. There are also cases where it's a little tricky to think about what the privacy object is. Like if you have thermal data or acoustic data, right? Like if there's no discrete record for an individual, so what does it mean to think about the effect of an individual on something, right? And there may be cases where the presence of an individual can only be determined by fusing information from multiple sources. We had talked about IoT space yesterday. Like no single sensor may tell you that Salil was here in this room, but by combining all of the different sensors, I can sort of basically tell that Salil was in the room, right? And like I went into Honeywell and they told me, we don't have personal data. Like, okay. And they said, yeah, we track basically for every light bulb, the timestamp when it was on and the timestamp when it was off. I said, okay, what kind of bulb do you have? It's a smart bulb, right? So it turns on when a person moves next to it and it turns off when the person moves away. And at night, if there's only one person, you can actually track where that person went, right? So there are cases where it's a little tricky to even think about what privacy, whose privacy, and so I think it's important to sort of think carefully about these problems when you're deploying differential privacy. All right, so now I want to talk a little bit about designing differential privacy algorithms, but I think you had a lot of talks about designing differential privacy algorithms. So I'm actually going to skip this part of the talk if I know how to do it, and I'm going to talk about the third part. Go there? Yes, it went there. Good. All right. Talking about estimates of error. All right. So let's say you have a data set. It's a distribution of tweets in some region in the US. That's a real data set. And let's say somebody wants to analyze this, and the curator who is analyzing this said, okay, I'm going to use differential privacy. I'm going to run a differential private algorithm and release a synopsis that looks like this that analysts can use. So they run the differential private algorithm. This is the output you get from this algorithm, right? It's a real algorithm. It's a real epsilon, reasonable epsilon. You can go on the DPCOM website and figure out what it is. And now an analyst comes along, he looks at this data set, he starts analyzing it, and he says, yay, I found a new result. My null hypothesis was the distribution of tweets should be identical to the population density. This data does not match the null hypothesis, therefore I have a new result. Let's write a paper. Right? What's wrong with this?
Didn't compensate for the noise.
I'm sorry?
You didn't compensate for the noise.
You have to compensate for the noise, okay? But something else is going on here. This is related to the it's basically the reason this data looks like this. In fact, we showed, I think this is the precise thing that somebody looked at this precise visualization and was like, wow, you have so much uniformity going on everywhere here. The uniformity is not coming from the data, it's an artifact of the algorithm, right? The algorithm creates these boxes, right, and then sort of uniformly spreads the data out there. It's not coming from the original data itself, right? And so the real question here is, how can we distinguish between artifacts of privacy algorithms and artifacts arising from the data? And before people pounce on me, artifacts in data can arise from many, many sources. The artifacts may be there in the data itself, right? But it could arise from missing data, record linkage, selection bias, sampling. These are very well studied. There's huge literature on all of this. But they can also come from privacy mechanisms, and we need more work here. And I was happy to see some people talk about this today, right? But you need a lot more work in this space, and we need more than 6 papers in the stats journals talking about this. Because the stats guys are really the guys who know how to do this stuff, right? So this, I think, is a very important area that we should not ignore, right? How do we take into account error? But also, how do we take into account biases that can be introduced because the algorithm makes certain decisions, right? If you know the algorithm, in some cases when you know the algorithm, you can sort of tell what the bias is, right? If the algorithm says, I am going to assume independence between these columns, you know what that bias is. But that algorithm was basically doing something complex, like doing some complex optimization, and it gave you that, right? It's sort of a black box algorithm. It's hard to know that it created those kinds of things, like a priori, just looking at the algorithm itself. Okay? In the last sort of few minutes that I have, I want to talk about sort of one use case of where we found that we needed to do this. We were working with social scientists at Duke who had access to data from the Office of Personnel Management. and they had it stored in this sort of secure server. And then the question they were asking was like, okay, you guys talk about synthetic data. Like, what would happen if you wanted to do an analysis on a synthetic data set, right? So they wanted to analyze wage gap between gender and race wage gap in the data across sort of careers of civil servants. And basically, they're asking if we did the analysis on a synthetic data set, what would it look like? And so nobody came up with linear regression till now, so I'm going to talk about linear regression. So this is the standard tool that they use. So linear regression is very simple. You have a bunch of explanatory variables, you have an outcome variable, and then you have some coefficients, and you model it this way. And clearly, you can't get a perfect fit always, so your goal is to sort of find something that has low error, and this error is sometimes called the residual, right? So what do people do with the real data? So this is what they do with the real data. They take a true database, they build a regression model, and they check whether this regression model makes sense. So they have some sort of diagnostics here, right? So what are these diagnostics telling? The diagnostics telling them, am I even having the right fit with this model? Like sometimes they're asking for how much prediction accuracy I have, like prediction error. But more importantly, they ask things about model fit, right? Is this linear model even the right model for my data set, right? And one way you can identify that is using what is known as plots of residuals, right? If your model is right, your residuals should be roughly normally distributed. Right? That's the correct assumption. And if it is not, then you will see sort of weird patterns here. If it's a nonlinear, you will see the residuals from a nonlinear plot. If your variance is increasing, depends on x, you will see some sort of a heteroscedastic. And you can sort of detect these from just the residual plot itself. Right? Yeah?
Just wanted to make it clear. I think we need to make a distinction between a model fit and model aptness, like the appropriateness of the model.
Yeah.
What you're doing here, first and foremost, you're actually checking for the appropriateness of the model.
Yes.
The assumptions, because in many of these models, they have assumptions. Yes. Because that can get potentially a good fit.
Yes.
But the model could be completely
wrong.
wrong.
Exactly. Exactly. Right. Thanks for clarifying. Yeah. Okay. So how would you do it on synthetic data? Well, you have a true database. You get a synthetic database out of the firewall, and you're looking at it. And then you run your regression model. And then now, what are you going to do? Are you going to do regression diagnostics on this? Well, it may be that if you did that on the true data, it might confidently tell us that the relationship is not linear. But in the synthetic data set, it might confidently tell us that the relationship is linear. Because maybe the model you used to generate a synthetic data set was actually linear. Right? So how do you have to break this? Like, there is nothing you can do at the synthetic data level unless you know very exhaustively what this process is to be able to sort of detect that this is actually what the truth is, right? And so one way you can solve it is to basically say, I will do the regression diagnostics. I will take this model and I will check whatever model aptness or model fit with the true database, right? I will measure that, but of course that has to be done privately. So you need sort of methods for sort of spending some amount of your privacy budget to do this kind of a verification, right? And so we designed some sort of simple regression diagnostics, one for sort of estimating private residuals. I'll talk a couple of slides about that. We also did for sort of looking for significance of the model parameters. And the first author on that, Felipe, will give a talk in the next workshop in April about that. But basically, the algorithm is pretty straightforward. Like essentially, what you're trying to do is density estimation, right? So you want to take this, you want to estimate the density. Some challenges that appear is like you don't have any bounds on these. Like you can get these residuals, and you're just estimating the density of the residuals, right? And then adding or removing one row adds or remove 1 point here. So it's not very sensitive. But of course, you don't have any bounds on residuals, so you need to sort of estimate these tight bounds on this. Otherwise, your error is just going to sort of become large. But you can do it. It's not too difficult. And so this is sort of the real residual plots, and this is what the residual plots look under differential privacy. And actually, we had the social scientists, we wrote a paper about this in Annals of Applied Statistics. We had the social scientists do their analysis on the real data. And then, but before that, also do it on the synthetic data, but then use these to verify to do the verification steps. Like, did the model that they trained on the synthetic data, does it actually make sense or not? And they were able to come to roughly the same kinds of consensus, right? So yeah, so the open questions really here are, and it's really a call to the statisticians, is like, what are statistical tests that can distinguish between artifacts of data versus artifacts of algorithm, and what kinds of error verification should we be doing, and how do you manage privacy budget for verification, okay? I'm going to finish in one slide and then I'll take your question, okay? So I want to end again with this checklist for deployment, right? So really think carefully about not just about how do you design your algorithm for differential privacy, and in fact I didn't talk about this today. It's really important to talk about all of the other aspects as well, right? Understand your uses of the data, because that is very, very important. Design your privacy carefully, and very, very importantly, understand how to interpret error and communicate it. Thank you. Get a question here. Yeah.
Sorry, I didn't understand how the synthetic data was coming into the model diagnostics.
The synthetic data doesn't come into the model diagnostics. So you are using the synthetic data to generate a model.
Yeah.
Right? And now you're asking, does this model make any sense really on the true data? Yeah. Right? So the synthetic data is used to generate the model, because that's all you have access to.
Why would you do this? I mean,
why would you do that? That's a very good point, right? So why would you do this? Because when the Census Bureau releases data, they don't know who all its users are, right? So they just release a synthetic data set. Now you as a researcher has two options. One option is you can go through 6 months of background checks and wait to run your regression model on the true data set.
I'm good with synthetic data.
Or use the synthetic data set, right?
That I'm fine with.
Right.
So then you're assuming, though, you can then come back to the real data to do the diagnostics.
All I'm saying is there has to be a way to do that diagnostics, because if you don't do it, then you may be making false discoveries.
So the census would have to allow some route for me to give them my model or something, and then.
That's what we think statistical agencies should do, right? If we are not able to estimate the error in a data-independent fashion. Like one option is if they're able to give sufficiently good estimates of error and bias without looking at the true data, that's great, right? In this case, we were not able to, and so we had to add this additional loop. Right? But of course, it leads questions as to how do you manage your budget with the verification, how do you do that? That's all good questions. Yes, who's the next question? Hi.
So there's a wealth of statistical literature on how to compensate for measurement errors in your data.
Yes.
And obviously, you could sort of, all the way from simply adjusting your beta coefficients from the attenuation because of the measurement error, all the way to Bayesian methods to denoise the data.
Right.
And so, I just wanted to point it out. You have the best thing about differential privacy and why the statisticians are looking at it is because it's public.
Yes. So please tell us how to do this.
Compensate for errors for missing data. I don't know what that mechanism is, and it's real problematic. But I will tell you how I put in the noise, and the statisticians will know how to deal with that.
Please tell us. We don't know, right? Yeah.
So I think here, there are two issues. One is the reason your model is bad from the original data, and is it an artifact of the way you have generated differentially private data? And I think, as we've seen in a couple of these talks, it could actually be the latter, because
of the algorithm.
That is the way this works.
Yeah.
But one thing, in something like this, you're basically trading off privacy, setting aside privacy budget to validate the models, which means you're getting worse data to begin with.
Yep.
And so you're more likely to get something that fails to validate.
I'm not sure, right? I'm not sure. So, okay, so one thing that I didn't talk about because I kind of skipped over a section is basically like there is a fundamental law of information reconstruction, which means that there are only certain things that you can actually do well on when you release data sets, right? So you can specify that these are the only things that you can hope to do well, right? But then people will still want to ask other questions. So what do you tell them? You tell them if that question doesn't match one of our questions, it's not going to do well, sorry, right? Or you could say I can have some ad hoc privacy budget for these other questions, right? For some ad hoc questions. And so one way to allow that is to sort of maybe have these sort of verification kind of engines. Yes. Yes, Shafi?
I'm not going to ask something probably doesn't make sense, but I'll ask anyway. So you've done the regression on the
Synthetic data. Yeah.
Now you just want to verify whether that regression model fits the real data.
Whether it makes sense, yeah, whether it fits the real data, or yeah, whether assumptions make sense or so on, yes.
Send over, let's say, the coefficients, the beta.
Yeah.
No.
No, you don't do that. You basically, you basically compute a function between the true data sets and the model. It's a function that takes as input the true database and your model, and it outputs something.
And the model is the betas.
And the model is the betas, yeah, exactly, yeah.
What I'm saying is if you sent it, if you did so you came up with some betas, and just you want to know whether your real database fits the beta.
Yes or no answer, for example.
So you want one bit answer.
One bit answer. Yeah, but that one bit of answer can also leak some information, so you still have to give some amount of privacy protection to that one bit of answer, because the analyst is the one who's seeing that one bit of answer, which is more than what they have seen from the synthetic data set.
But if the analyst can sort of prove that he got those betas using some method of analyzing the synthetic data. So it's a little bit like we have these CCA attacks, right? So if you could prove you're learning nothing new except that...
if you spend addition...
You're worried about the
yes.
The fact that it fits this model
Yes.
gives information about it.
Yes.
However, in a sense, that's all it needs, that it fits it. That would, there was some sort of guarantee that you knew it anyway, you're just trying to verify that it's correct?
No. You didn't know it anyway. Like if you knew it anyway, you wouldn't spend extra budget to verify that it is correct.
So this really is a way to distinguish your synthetic data from the real data. So it's not about verifying that the model...
Maybe the name verifying is not a good name, but essentially what you're trying to see is you are getting more information from the database. Yes.
It seems to me like there's two scenarios, at least in my head. One is that you really want to know whether your database fits this model, and that in the true at heart analyst, honest, that's what they want to know.
Right.
And then there's an analyst as an adversary,
right,
who actually is trying to find out the differences between the synthetic data
right.
and the real model.
Okay.
So if you had a way to somehow...
I mean, we think of the analyst as an adversary. So anything that analyst can do, we'll take this offline maybe.
Yeah, trying to
leak information.
No, distinguish the synthetic data and the real. It's trying to find something about some data subject in the real.
Right. So the security guarantee we want to give is not about the entire database itself. It's not that we don't want to leak everything about the entire database. What you want to protect is individual rows in the database. It's okay for the distributional information to be learned, right? What you want to hide is individual rows.
I suggest we take other